So, but it gets more complicated than just hashing. To create a blockchain block, we hash more than once. And I'll show a diagram in just a minute, but it's very interesting, at least to the nerd in me, that you hash and you get a string, you hash some more data, you get another string, and then you can put the two strings together in a new hash. And you can do that over and over and over again. And so you have hashes gradually consolidated until you have one final hash for the transactions. And that final hash is called the root. Now in my view, that's a dumb word. It's the Merkle root at the top of the tree. The fact is, roots don't generally grow at the top of the tree, they grow at the bottom of the tree. But if you look at the literature, it's more complicated than that. The Merkle root is up here at the top. Now, the other thing, I mean, this is really the definitive slide. Well, there's one other one that is also definitive, but this gives you the sense of how a block is constructed. A series of data batches that are then hashed. And by the way, as I said, the computer world likes powers of two. So if you know you're going to combine two things and then combine two more and then combine two more, you really need to have a group that starts out with a power of two. So in this case, if there are only 5 batches and you need to create a Merkle tree, you need to replicate that 5th batch for 6, 7, and 8. So 7 and 8 come together, 5 and 6 come together, and it turns out this hash and this hash will look exactly alike. But of course, when that hash is created, it won't resemble anything else. And so you have this cascading hashes where you get all the way to the top, and it's the Merkle tree root. It's the final hash after doing all of this stuff. But wait, it gets more complicated than that. The blocks then also get a timestamp and some identification to help it be unique. But it gets more complicated than that. The next step is to link a block, because we've shown it with little arrows that point back across the chain. We point to the previous block. And this is, again, this is part of the cleverness. The new block uses the hash of the old block, so as part of its identification, which means that if anything along the way changes a block, it changes the hash, and the hash then is no longer legitimate in the block in the header. So you can know immediately if a block chain is compromised, because the chain then fails. But gee, that sounds terrible, except there are hundreds of chains all replicated with the same data. So if someone screws with my chain and breaks it, I can go out and ask other members of the network to give me their copy of the chain, and then I'm back clean again. So hashing the previous block and using it as part of the new block is amazingly creative. So this is the second slide that really essentially says it all. We've got transaction data in batches. You do a bunch of hashing with a Merkle tree. We combine hash. These two batches get hashed into that. These two batches get hashed into that. These two hashes get hashed into that, and that becomes the Merkle root. So this is now the hash of block n+1, the block we're working on. But if we go back upstream, there's also the hash of block n and n+1. So we look at the hash of block header n, and that becomes part of the header of n+1. Again, it probably sounds more complicated than it is, but it's just like if I want to know the members of a string or a chain, I put in the current header the one most recent one. So if you were thinking about a street and addresses on the street, you could say, I want every address to actually have a sub-address that points to the previous address. So I can just go through address by address and go absolutely down the street, one address at a time. So this is the one we're working on. This is the last one and the one before that. And all of it has incredible computing power necessary to do the hashes. So as of this point, we, I think, can understand mining. The first part of mining is to take the data in the batches and start the hashing mechanism. You just do it over and over. But that's pretty deterministic. That is, I know exactly what to do. I take this batch of data, I send it to SHA 256, and I have a hash. I take this next set of data, send it through SHA 256, and I have a hash. Then I take these two and I hash. So there's a lot of computing power required, but everything is straightforward. You know exactly what to do. At this point, it's all computing power and it's very clean. You know exactly what to do. Take this batch, hash it. Take this batch, hash it. Take the two hashes, hash them together. Take the next two hashes, hash them together. All the way up to the point where I have hashed everything in my database, and now I have the Merkle root. Again, root being a strange term because it's really at the head of the chain. So again, to repeat a little bit, if you know what the old hash was and someone changed the transaction, it would create, as we saw in the hello dot, hello small h, a totally different string. And so it would break the chain. And I said, you could no longer go backwards on the chain. So any change in the chain breaks the chain. So by hashing within a block and having that tied to the next block, then you have guaranteed that any change in a block is immediately visible. That is, the chain breaks. So if I was to try and overcome this with just raw computing power, you can see I would have to open a block, go to the block before it, go to the block before that, and I'd have to redo all of the calculations all the way back along the blocks. And it would take impossibly large amounts of computer power to do that. We'll see in a minute how much power it takes just to create one block, much less having to go back with along and do 1 million blocks. But